Hey class, in this lecture, I'm going to cover some GIS basics, terms, definitions, concepts. I want us to all get on the same page before we go forward and build our skills throughout the semester. So the learning objectives for the lecture are 5 in number. So we're going to define some basic GIS terms, talk about how a GIS works qualitatively. I'm going to talk about the different things that a GIS can do. We're going to talk about 2 different GIS data models. So a data model is just a way that the information in the GIS is represented. There's one data model called a vector data model and one called a raster data model. We'll get into those when we might use them and their pros and cons. And then we're going to talk about some GIS data types that you might encounter in the wild when you're downloading GIS data, or if you're preparing GIS data on your own from scratch, you'll want to be familiar with those data types as well. So let's start with some basic definitions. What is a geographic information system? One of the Esri textbooks, Getting to Know ArcDesktop, says that a GIS allows you to study and explore everything about a place. In the Gimmon chapter that you all read, he says that a GIS is a multi-component environment used to create, manage, visualize, and analyze data and its spatial counterpart. And I think a GIS is simply a tool that helps you think better about and act upon spatial problems, concerns, and challenges. There are some common elements of the different definitions, right? Each of them refers to space or place. I think it's helpful to think about a GIS as bringing together, the way that I often describe it when I'm talking with regular folks is that we have maps and then we have data, right? So we have some kind of spatial component that we're describing or analyzing or visualizing, as Gimmon says, and then we have some information about that place or that location in space. So it could be a city, a county, a neighborhood, a census tract, a business, a restaurant, a store, anything that's located in space, and we have some information about it. GIS, ArcGIS Pro, QGIS, whatever, is going to help you understand things about space and the underlying data and the various phenomena that manifest within it. It's helpful to show some examples about what a GIS is for, since definitions can sometimes be somewhat abstract. So a kind of basic use for a geographic information system is just to provide a reference map. So this is a map from the U.S. Geological Survey showing state boundaries in the United States, state capitals, the location of interstates. If you were navigating the U.S., say you're taking a road trip, this would be a very useful map to have. It just shows where things are located in space and where they are relative to one another. So a basic function of a GIS could be to just provide reference information about space. Probably not the highest use of a GIS, and one that we're not really going to dive into in much detail in our class, but certainly a use. Now, in the Gimmon chapter, he talks about a different type of use for a geographic information system, and this is to visualize spatial phenomena. So we want to understand how phenomena that are located in space might be related to one another. So he talks about this conflict index that's calculated for different countries in Africa. And he says that, if you just wanted to know the top 10 countries that had the highest conflict index, you could just put all the values in a table, sort the table from greatest to least, and pick the first 10 rows, and then you've answered your particular question. Now, what that table wouldn't show you is how the conflict index is related across different countries. When we plot them on a map, we can see that in fact it seems like there's kind of this high level of conflict index through Central and kind of East Africa, and it dissipates as we move to the west somewhat. That might be a phenomenon that we want to study. We might want to explain why those things are happening. We could look at differences in governance here. We could look at differences in the economic situation in these different countries. We could look at differences in kind of authoritarian versus democratic governance styles as well. So this is a really key use for a geographic information system. This type of map is typically called a choropleth map or a thematic map. And we're using some actual shapes that are located in space, in this case African countries. But we're visualizing some properties of those shapes, in this case the hue that we're using to display the country, according to some value in an underlying attribute of that particular feature. So here it's the value of the conflict index. So in contrast to the reference map where we're showing things in space, right, their precise locations, here we're saying there's this phenomenon, a conflict index, that we're saying obtains at the level of the entire country. And then we're going to visualize that conflict index at the level of the country. So it's not like the conflict index is located at a place. The high level of the conflict index in Sudan is located in a place, but it's a property of that place. And we can look at how the value of that property is related across a number of different spatial units. We'll be making approximately 1 million choropleth maps during this class. And this is often a function of a geographic information system that we want to use. So we've got one attribute, we're visualizing it, we're looking at some spatial phenomena. We can also look at combining information across many different layers. So here, this is another use of a GIS, which is integrating and summarizing spatial data across layers. The information here is taken from an academic paper looking at creating a suitability index for photovoltaic generating capacity. They've got a number of different characteristics here in these layers on the right, things like dusty days, cloudy days, distance from roads, and they're integrating them all into a single index of suitability. So green, lighter shades or darker shades of green indicate less suitability, and these shades of orange and red indicate greater suitability. The color ramp here is a little counterintuitive. Typically you want the kind of good end of the scale to be associated with green and the bad end of the scale to be associated with red. So here, if you want to cite PV in this particular location, you would probably want to have the green colors associated with the places that are excellent and the red colors that are red colors to be associated with places that are poor. We'll get into a little bit of color theory and thinking about color ramp design later in the course. Okay, I would argue that the highest value of a geographic information system is to tease out patterns that are not easily visible in the original data. This is a really good example of a spatial data visualization created by a civil engineer named Charles Menard in the 19th century. So he was looking at the strength of Napoleon's army as it marched from west to east from the Poland-Russia border over here to Moscow. And the width of this peach-colored bar was the strength of Napoleon's army, measured in terms of the number of soldiers that he had as it marched from west to east. And then the black bar here is the strength of Napoleon's army marching from east to west. And the bar corresponds to the actual locations that they visited. And we've also got information about temperature here on the return journey. So you can see that temperatures were pretty severe. They also had various supply chain issues with keeping folks fed, clothed, and housed along the way. That led the numbers to dwindle from about 700,000 to about 10,000 or so on the return. So there's lots that you can glean from this image in a very quick, intuitive way that you could potentially get the same results just from looking at summaries of tabular data and summarizing them in various ways and making sure that they're arranged properly. But this visual, for me, is very powerful. And so we want to strive to create data visualizations like this one from the 19th century image of Menard. Okay, so how does a GIS work? We kind of know a bit about what it can do. We have a working definition. At a very basic level, a GIS is simply helping us visualize and analyze spatial data in layers. And the layers that we're looking at are all referenced to locations on the Earth's surface so that we can line them up. And we know that when we're pointing at, say, a particular location on this elevation layer, that particular location corresponds to the same location on this aerial imagery layer, say. So it's super important that things line up. Layers are really important. You'll sometimes encounter older terminology about layers. So in earlier versions of Esri's products and other software, layers were referred to as coverages and also themes. And often it's helpful to think about organizing your data in such a way that every layer is kind of, it contains elements that are related to one another. So if you've got a transportation layer, you probably want that to include local streets, state highways, county roads, maybe interstate freeways as well. You put those all in a layer, store them all together, and use them in your analysis. You probably wouldn't also include rivers on that layer because it's going to be, you're going to run into issues when you actually want to conduct your analysis because you often want to conduct analysis about a particular feature of a place. You want to know something about transportation infrastructure or something about hydrology. And you'd be unlikely to want to store those two things together. So that's why this term theme is helpful, because it embeds this idea that everything within a layer is kind of related to one another in some way. It's just helpful for data organization as well. If you have a colleague that's working in transportation planning, you don't necessarily need to send them a couple of layers, or one layer that contains transportation and hydrology information together. Okay, so layers I mentioned are explicitly referenced to locations on the Earth's surface. This is super important. We will sometimes run into issues where that reference information is missing, and it's going to create various types of problems. Layers generally contain two types of data. So there's spatial information about the features that we're looking at, whether they're roads, landfills, air quality monitors, creeks, whatever. So we know where those things are. And then we have attribute data about them. So we know some properties of those things, like how much water is contained within a particular reservoir, or how many lanes are on a freeway, or the speed limit of a local road. There's no limit to the number of attributes we can describe about a particular feature. The layers can be represented using two data models. So there's a vector format or vector model, where we can, the kind of underlying idea is that every spatial phenomenon that we're interested in can be represented as one of three things, either points, lines, or polygons. And then we can also have a raster format or raster data model, where we're representing things in terms of the value of a pixel or a cell across space. And I'll go into more detail in a minute about those two. But we can have a map that contains many layers. So we've got all of our themes linked together. We can bring them into a map for visualization purposes. So this one is showing coal basins, electricity generating, or rather electricity transmission lines, and then electric generating capacity. A couple things are missing from this particular map. So we've got a legend that tells us what all the map symbols mean, what all the colors mean. That's great. We don't have a north arrow and a scale bar, which we're always going to want to include in our maps. Okay, so what are the types of phenomena that we want to represent? I mentioned the two data models for our layers, and those two data models usually map onto two different types of phenomena. So one is a kind of discrete things that have well-defined locations in space, well-defined boundaries. These are things like neighborhoods, air quality monitoring stations, roadways, etc. So we can kind of point to a particular place. I'm in Sutton Hall right now. I can point out my window at Guadalupe, and I know where Guadalupe is. I know where the drag is. It has a defined boundary, right? It's the right of way of the street. There's another type of phenomenon that we often want to represent in a GIS, and that's a continuous spatial phenomenon. These literally exist everywhere, right? So these are things like elevation, air quality, wind speed, and noise. No matter where I'm standing on the planet Earth, there is an elevation associated with that location, right? I'm some number of meters above or below sea level. I can measure air quality. So I can measure parts per million of carbon monoxide, say, at every location, that there's some concentration of CO literally everywhere. And so we'll use different types of data to represent these two different phenomena. So the discrete data map onto a vector model. I mentioned already that all the features in the vector model embeds this assumption that all features in the real world can be represented as polygons. So these could be things like parcels, cities, counties, lakes, right? They have established boundaries. We can draw the boundary and represent it as a polygon. Some spatial features can be represented as lines. So these are things like streams, streets, and sewers. Roads are often represented as lines as well. And then points. So things like trees, fire hydrants, airports, or cities. And I put a little asterisk here because cities is in the points category as well as the polygons category. And so you can represent a city either as a point or a polygon, right? If you're looking at a small scale map that's really zoomed out, you might represent cities with points, right, on a reference map, say, and that might be sufficient for your purposes. But if you've got a large scale map that's really zoomed in, you might want to represent a city with the polygon, right? In a lot of the analysis that we do, we often are interested in representing cities and neighborhood boundaries as polygons because we want to do some analysis on the boundary. We want to know about how many things or what types of things are located within a city or within a neighborhood or a tract or whatever, rather than just visualizing it, in which case a point might be more appropriate. But the point of showing cities here and here is just to let you know that there's no hard and fast rule, right? We can sometimes we could represent a road using a polygon, for example. We don't necessarily need to use a line. Whether you represent it as a polygon or a line is going to depend on your analysis needs. The raster model, again, usually used for continuous data. In the raster model, we don't have polygons, lines, and points. We just have a grid of equally sized cells that's laid out over space, and every cell gets a single value based on whatever characteristic we're measuring. We're trying to quantify with that raster. So it could be temperature, wind speed, land use type. But we have one cell. The cell has a defined dimension. It might be 10 meters by 10 meters. It might be 5 kilometers by 5 kilometers. And within that cell, it gets one value. So you can start to see that the raster model, there's going to be some loss of detail, right? If we've got, say, a 10 by 10 meter grid, we're associating one air quality measure with that 10 by 10 meter cell. But in the real world, if we actually go around and measure air quality at different points in that 10 meter square, it's going to be different. So we're accepting that there's going to be some loss of specificity with the raster model to get some of the benefits that the raster provides. And here's what the things look like kind of lined up all together. So I've got some vector data here, customers identified as points, presumably using their home address, city streets, and then residential and commercial parcels. Those are overlaid on some kind of raster data representing elevation and land use. So the type of data set you're going to use, it's often going to depend on the phenomenon that you're studying and your analysis needs. But there are some pros and cons associated with each. So vectors are nice because they maintain accurate geographic representation of the features. All that means is that we have explicit latitude and longitude coordinates for all of the things in our vector data. So if we've got a data set of, again, air quality monitoring stations, we know the precise latitude and longitude coordinate of where those things are. So it makes vector data are more useful for cartography. If we're making any kind of map, if we want to summarize our results in some way, we're probably going to want to use vector data. Raster data are harder to visualize and harder to interpret. It's harder to interpret visualizations of raster data. And it's generally not possible to store continuous data in a vector format unless you had something like an evenly spaced grid of points. But in that case, you probably just want to use the raster data because it's going to be faster. So the nice thing about the raster data is that it's very lightweight and efficient. All we need to know is where the kind of bottom left corner of the grid is located, the size of the cells and its orientation, and then we can identify where each cell is based on its location in the matrix, right? How many cells over and up it is will tell us exactly where it is on the Earth. We don't need to know the precise geographic coordinates, which is really nice. The cell size limits spatial resolution. So I kind of already mentioned this, but if we've got a 100 meter by 100 meter grid cell, there's probably going to be some variation in whatever spatial phenomenon we're looking at within that grid cell, but we're just assigning a single value to it. Usually it's fine, right? We size the raster to capture a reasonably accurate value of whatever phenomenon we're studying, but we are certainly losing some resolution. And then we only have one attribute available at a time, right? We have a raster that represents temperature, elevation, air quality, and we can only represent one thing at a time. We can combine things in various ways through some of our analysis routines, as we'll see when we study rasters later in the course. Usually what will happen is that you'll be kind of limited by your input data source. So you might download global temperature data in raster format, and then you need to associate it with the neighborhood level. So you'll undertake some kind of conversion workflow to go from raster to vector. So there's no hard and fast rules here. You can read a little bit more about the differences at this Stack Exchange link here. In Esri's language, they refer to vector data as features and raster data as surfaces. Again, both of them have locations. Features are linked to what is often rich information. So in the screen capture video, I'll show you an example of an attribute table. So every row here in this particular set of features is an individual feature. And then it has various attributes that are describing properties of those features. So in this case, these are urbanized areas that I was looking at in a brief study I was doing of Cancer Alley in Louisiana. And these are just some census definitions. So in this particular layer, I've got this urbanized area shape. I can open up the attribute table, and then I can see all the properties, all the information that I have about that shape, including water area, land area, and some census identifiers and codes. The features are also related to one another. This is a set of layers showing water distribution, infrastructure, and valves. So if you were working in some kind of control room at a municipal water distribution facility and a valve went down, you could immediately see, okay, what are the properties that are going to be affected? Where do I need to dispatch my crews to? So the relationships between spatial features often help us glean insights when we're working within a GIS. In terms of surfaces, I mentioned these are linked to a single piece of information. So here I've got some data from a digital elevation model, and I've just clicked on one of the cells, and you can see that I've got a value here. The pixel value is 197. That could be meters above sea level. It could be feet. Depends on where you got the data from, what the metadata tell you about what the units are. Okay, all of these layers that I've been talking about, all these kind of forms of data come in different file types and different data types. So there are a couple different formats that we're going to work with throughout the course of the semester. One is called a file geodatabase. So a file geodatabase is a kind of container for spatial data that we access only within ArcGIS Pro. If you look at it within Windows Explorer, it's going to look like a folder that has a .gdb extension, but when you click into it, it's going to have very strange file names and extensions. You're not actually going to be able to work with any of the data through Windows Explorer. You have to use ArcGIS Pro. So file geodatabase simply contains information. It can contain vector data, raster data, or other types of data. You can encode topologies, which are rules about how different features can interact. Our vector data, there's two types of data that we're going to be working with. Any file that contains vector data can be referred to as a feature class. So there's one that's very popular that Esri created to be a kind of open source way for sharing feature information. It's called a shapefile. You might have seen or heard of a shapefile. You might have worked with them yourself. The term shapefile is kind of a misnomer because typically when you download a shapefile off the internet, it's going to be a zip file. And when you unzip it, it'll contain a number of different component files. So a shapefile is actually composed of many component files. We'll get into that in more detail. And then you can also store a feature class within a file geodatabase. You can have a file geodatabase feature class that has to be stored in a geodatabase. There are lots of other vector representations as well. GeoJSON is one that I like. It's a plain text way of storing vector data. There are lots of different raster formats depending on the type of data that you're working with or the folks who created the data set. They might have different standards and formats that they use. So there's a link here you can go and look through. There's a thing called a project file that's going to be pretty important for working with ArcGIS Pro. So this ARPX file is a project file. The PPKX file is a project package. ARPX file is your project file. It's going to point to all of the key pieces of information that have to do with a particular project. And you can think about a project in ArcGIS Pro as representing a kind of discrete piece of work. In our class, you're going to be working on labs. Each lab is going to be a project. Your final project will be a project. Your PR that you eventually work on will also probably be a project. And the APRX file is going to maintain key information about your project. In the screen capture, I go into a little bit more about what a project is. There's also an antiquated or archaic file format called a map format with the extension .mxt. The MXD was used in prior iterations of Esri's products, so on ArcMap and ArcGIS Desktop. Within ArcGIS Pro, we have an option to have multiple maps associated with our project. When working with ArcMap, we were typically working with one map at a time, and it was somewhat limiting. So you might encounter MXDs. We're going to use them a little in the class, but typically we'll just be importing them into ArcGIS Pro, and they'll become just one map in our project. Okay, so we defined some basic GIS terms. We talked about what a GIS is, talked about vectors, rasters, talked about how a GIS works by bringing information into a kind of common space where there is a consistent set of geographic data linked to every piece of information that you're bringing in so that we know that everything lines up whenever we're conducting visualization or analysis. We talked about multiple things that a GIS can do, from making a reference map to helping us glean insights that are not available from the underlying flat data. We talked about vector and raster models, and then a number of different GIS data types. So I hope this gets us on the same page, and there's more information available in the screen capture associated with this lecture.